Hello everyone, my name is Ling and I'm currently a PhD student in the University of Minnesota under the guidance of Professor Tian. I'm also doing some research in Alibaba Group in China on the on-demand delivery. In this talk, I will introduce our experience in building a wireless beacon system in the wild across 3 years. On-demand delivery is nowadays a common service around the world. They provide great convenience, especially during the pandemic. In the US, we have DoorDash, Uber Eats, and Instacart. In other countries, we also have similar services. In China, there are two major companies, Ele.me and Meituan, and Ele.me is an Alibaba subsidiary company. In a delivery process, there are 4 key timestamps. First, the courier accepts the order assigned by the platform. Second, the courier will arrive at the merchant's shop. Third, the courier picks up the meal and leaves the shop. Finally, the courier delivers the meal to the customer. Especially, many of the shops are in the multi-floor malls, which makes the process even more complex. Well, in this process, why do we care about the accurate arrival time at the shops? Because many upper-layer applications need this information. Here, we show 3 applications. First one is order dispatching. The arrival information can be used for localization and time estimation in a learning-based dispatching model. The second is the overdue order investigation. Usually, we have a time constraint for each order. If the order is overdue, we need to know the reason. The couriers comes late or the meals are not ready, so that the process can be optimized. The third is order progress demonstration. We use courier's GPS and timestamps to display the order progress on customer's app. In industry, we already have 2 solutions. One is manual report. But we found that some couriers forget to report and some couriers tend to report earlier for their performance. The other is smartphone GPS, but GPS is inaccurate in an indoor environment. The real-world solution is a combination. We have a reportable area. If the courier reports within the area, we think the report is accurate. However, this hybrid solution is still not accurate enough. In research, arrival detection can be defined as an indoor localization problem. The state of arts can be categorized into 2 classes. One is infrastructure-based. Dedicated devices are used as anchors like Wi-Fi AP, LED, RFID, and QR code. However, these methods have limitations like deployment cost, additional hardware modification, restriction on smartphone hardware, and additional manual effort. Another category is infrastructure-free. Fingerprints of acoustic, magnetic, AMU, or electromagnetic are collected at the anchor location and compared with the data collected by the target for localization. These solutions do not need physical anchors, but need set survey to build a database, and the database have to be updated frequently because the indoor environment is highly dynamic. Therefore, we choose Bluetooth beacons because it's easy to deploy, accurate enough, transparent to couriers, and the cost is acceptable. From now on, I will focus on our aBeacon system, short for Alibaba Beacon System. The workflow is as follows. First, we deploy 1 beacon device in each shop and bind its ID with the shop ID on the cloud server. Then, the beacon device advertises the ID tuple continuously. When a smartphone approaches the beacon device, the messages will be scanned and uploaded to the server. Finally, we will detect an arrival event through mapping. On this page, I will give you a big picture of our deployment timeline. The red line is the number of active beacon devices, and the blue line is the number of orders served. In June 2017, we conducted a conception stage to understand whether a Bluetooth device can detect the courier's indoor arrival accurately. we bought 3 types of commodity devices and attached them side by side in each of 18 shops. At the end of the stage, we found that the Bluetooth devices can detect 98% of arrival events. Then, we move to the customization stage. The major purpose is to test our customized aBeacon device with lower cost and longer life with A/B test. In each of the 200 shops, we deployed 1 customized device and 1 commodity device side by side. The results show that the customized device can achieve similar performance. Then, we started the citywide deployment in January 2018. From the spatial heat maps, we can see that the deployment covers most business areas in Shanghai. Beginning from March 2018, the system was fully operated. During the operation, we can observe some fluctuations like server issue, Spring Festival, and the COVID-19. Starting from November 2019, the number of devices dropped quickly due to the capacity of the battery. In March 2020, the system retired. In the next several slides, I will introduce the performance and some lessons learned. First, I will introduce the utility. We choose the overdue ratio reduction as the utility metric. Here, overdue ratio means the ratio of timeout orders among all orders, and the reduction measures the improvement introduced by aBeacon system. We choose this metric because it can be viewed as the monetary saving brought by aBeacon system, since the platform needs to pay for each overdue order. To calculate the cumulative gain, we conduct A/B tests with shops without aBeacon devices. In this plot, we can see that we reached the break-even line after 12 months. An interesting observation is that in higher floors or basements, the beacon devices bring more utility. We believe this is because GPS-based method fails to give accurate time estimation for those shops, so it improves the data quality significantly. We use the reliability metric to measure how many arrival events can be detected among all events. The reliability can be calculated offline based on our accounting data. It is estimated that we can reach the break-even line 6 months earlier if the system is 100% reliable. The reliability is impacted by several factors. The first is the staying duration between the arrival and the departure. As shown in this figure, longer staying duration improves the reliability, but it does not change much after 5 minutes. The second is the smartphone hardware. The average reliability is 75% for Android and 85% for iOS, but the reliability varies for different brands of Android phones. From the observations, we learned that even for a simple application like arrival detection, the reliability is far from guaranteed in the wild due to many factors. We also found many beacon devices died during the operation stage. To understand the reasons, we made a scatter plot of device lifetime and the shop lifetime for all devices. We can observe 2 clusters of device deaths. The first cluster is around 2 years after deployment. This is due to the battery capacity, as expected. The second cluster is around the diagonal. That means the beacon device is dead together with the shop closing. For points above the diagonal, the devices died before shop close or battery running out, possibly due to the intentional or unintentional wrecking. The interesting part is those below the diagonal, which means that the devices are alive after the shop close. From these observations, we got a lesson learned. That is, battery may not be the major constraint for mobile wireless devices, since 40% of devices survive longer than the environment. It's a waste of investment if a device is alive but cannot serve its purpose. Here we select some key lessons and give some implications. The first lesson is that physical devices fail earlier than expected. This forces us to rethink the cost of hardware deployment. And the implication is that it's better to adopt or reuse existing devices. The second lesson is that wireless devices are not reliable for regulation applications. Our implication is that hybrid solutions are needed, like a mix of Bluetooth, GPS, and manual report if you need regulation applications. The third lesson is that device lifetime are significantly affected by the environment. Our implication is that if you really need to deploy hardware, it is better to conduct environment investigation and provide adaptive battery design. Based on the lessons learned and the implications, we are working on the next generation of aBeacon, aBeacon Plus. In aBeacon Plus, we utilize merchants and corporate smartphones under their consents and the additional Bluetooth transmitters, and designed mobility models to decide the corporate locations given their encounters. The new system has no hardware or deployment cost, no lifetime or battery worries. For those shops cannot be mapped to merchants or corporate phones, we will still deploy Bluetooth devices to provide a complete hybrid solution. We share 1 month of data we collected in the aBeacon system. 3 datasets are released. Courier report data for each order, aBeacon sensing data with timestamps and signal strengths, and courier trajectory data. That's all for my talk. Thanks for listening. I'm happy to share my work with you. If you have any questions, feel free to ask now or contact me later. Thank you.